Good day, everyone. Please come around if you want to have a little presentation on pipeline integrity monitoring solutions using optical fibers. This is a passive monitoring technique that sees detection of leaks and other activities on pipelines. Now, this technology in particular can be used on above-ground pipelines, below-ground pipelines. They can be retrofitted to existing pipelines, or they can be deployed new with any new deployment of a pipeline. What I'm showing here on the right-hand side, this is a view of beautiful Perth City, where we operate 30 kilometers of pipeline monitoring, and a lot of what I'll be talking about is about this particular deployment. Now, can you spot the problem? In general, 4 to 50 pipeline breaks occur per 100 kilometers per year around the world, depending on where you are. And this varies within country, this varies just about in every way. So this accounts for roughly 10 to 70% non-revenue water for a lot of these utilities or other entities that manage their water. That's an enormous loss of profit when you're actually losing that much water. And more than 90% of these breaks are reported by the public, as in these utilities do not in fact see any of this on their own internal networks. There isn't anything being flagged internally. This is just being reported by somebody passing by. Now, the major causes of these failures are due to underground well, it's actually quite a challenge because a lot of these pipes are in fact underground, so you don't see this. It's only once they fail and they produce some sort of surface expression, generally in a big way, that somebody sees that something's happening. 50% of these are due to accidental strikes, poor construction, age, and ground movement. Swelling soils, other geohazards such as karsting tend to break these pipes. There's a lot of different ways to break a water pipeline or an oil and gas pipeline. The risks for this are there's a major strain on water supply, environmental and property damage, operational interruptions, and loss of public trust. It might seem a little bit insignificant, but loss of public trust actually it trickles down and it creates a much larger effect. The traditional ways of finding leaks look exactly like this. You put your ear on the pipe one way or another to listen for a leak. And now this leak may be occurring 5-10 meters away, and you might not pick it up. 100 meters away, you certainly won't pick it up under this methodology. And if you have a very large network, you effectively need teams of people just like this to put an ear on the ground all over the city, all over remote regional areas to try to find these breaks. If you do this over hundreds of kilometers, you can see how unscalable this becomes. This is incredibly difficult to do, certainly with any level of consistency. Now imagine if you can listen to every meter of a pipeline every minute of every day. And I'm talking about literally listening to every meter of this pipeline. Let's stretch that, and let's say that we want to do this with the simplicity of a standard fiber optic cable. It may be pre-existing, or perhaps we have to deploy it, but just a standard fiber optic cable. There is nothing on this that is going to break. These cables themselves are quite robust. Once they're in the ground, nice and safe, not much happens to them. Well, this is exactly what we do. Terra 15 produces these treble DAS interrogators. This hardware device, in fact, is what makes this magic work. This hooks up to the fiber optic cable, and it turns that cable into thousands and thousands of sensors. Let's call them microphones. Pair that with Assure SRV, which is our software that allows customers to visualize this data and visualize what's happening in a simple red light or stoplight fashion. If it's red, there's a problem, stop. Yellow, something's going wrong, maybe we need to think about what we're going to do. Green, oh good, nothing to worry about, let's plug away. Let's try a little bit of audio here if we can. Does not come through. It's a little bit loud in here, so let's just say that we heard that. This, in fact, is a jackhammer that is being detected along the fiber optic cable, and if you were listening to this, if the sound was playing, you'd actually hear the of a jackhammer. of a water leak as well. This sounds like hissing and spraying, a little bit of bubbling and gurgling as the water drains through the soils. So we can quite literally listen to every meter of this pipeline. We like to say, if you can identify what this is with a human ear, you can classify it via an algorithm. You can pull the data apart, decompile the spectrum, and say, well, this is what's happening at this particular location. Now, this is incredibly versatile. This is not just water pipelines that we're talking about. This technology can be applied not only to water pipelines, but to mining processing fluids. Mining pipelines generally tend to contain suspended solids, caustics, all sorts of nasty stuff, saline waters, just stuff that you really wouldn't want leaking going into the environment. Additionally, this technology works for underwater pipes. If you're in contact with a pipe and this pipe is pressurized and springs a leak, you will see an acoustic response being produced even underwater. You can also use this for oil and gas, hydrogen, energy, processing plants, you name it. If the pipe is pressurized, you can use our solution for that particular pipeline. Now, how does this work? What is the magic that makes this solution work? These treble DAS interrogators manufactured by Terra 15, they effectively send pulses of light into a fiber optic cable. These pulses of light, as they travel down the fiber optic cable, encounter imperfections that are naturally found just in the process of creating a fiber optic cable. When it encounters these imperfections, light gets reflected back to the interrogator, and we effectively capture a fingerprint. You can think of these little dots as being a fingerprint location. Send subsequent pulses down the fiber and agitate the fiber one way or another, and you have a vibration sensor or a microphone. So I mentioned listening to every meter. Well, that's exactly how we do it. Here's a proof of concept that we did early stages for a water corporation in Perth. There's a fiber optic cable about 2 meters away from this particular pipeline, and the engineers open up a hydrant. As he opened up that hydrant, you see a vibration response start at 1.7 kilometers. As the engineer closes that hydrant, that vibration response disappears completely. Turn it on again, and off it goes. All right, there's other activities here as well. There's actually a car driving down the road and some other work being done further down the fiber. We can identify all these things in near real time and flag it to interested parties. It might be the utilities themselves, it might be a repair company. In some parts of the world, it might be a security company because you're more interested in the third-party interference. Now, what makes these interrogators special, or what makes these devices special for this application? Well, they're designed to be the best performing interrogators in the world for infrastructure monitoring due to this very unique patented construction. It makes us really, really sensitive to the higher frequencies. It makes it ideal for leak detection, infrastructure and asset health, microseismic monitoring, falling into the geophysics space, high-resolution seismic, and surface wave studies. Now, to explain the plot here on the right-hand side, I'm showing a couple of lines, 2 lines really. This blue line at the top, this blue dashed line, that represents the traditional way of building one of these DAS interrogators. And when they report their instrument self-noise and strain, it's a white spectrum. So it's a flat response with frequency. Our interrogators are built a little different. And they actually have a decreasing instrument noise with increasing frequency. That, to give you an indication, say at 1,000 hertz, we're about 10 times more sensitive than the nearest interrogator. Now, pipeline leak detection generally occurs within frequencies greater than 100 hertz to 2 kilohertz, well within our competitive advantage for this particular application. Now, this is actually inversely correlated to sensitivity. So instrument noise, and again I'll say that again, instrument noise is inversely correlated to sensitivity. As instrument noise goes down, sensitivity goes up. Okay? So if we're talking about sensitivity at 1,000 hertz, we're far more sensitive than any other interrogator in the world. 100 hertz, that's absolutely well within our wheelhouse as well. Now, this makes this technology ideal for dual use cases. Geophysical use cases, to be precise. Now, if you have this fiber in the ground buried next to a pipeline, why not use it for geophysical studies? Well, That's actually something that we've done, not because we set out to do so, but because coincidentally we're able to detect a lot of geophysical activity on these, on our fibers in the city of Perth. Now in the city of Perth, we run about 30 kilometers of pipeline monitoring, and this is in the densest precinct of the city, downtown area, very busy, lots of buildings, lots of cars, lots of people, lots of noise. Even still, we've been very, very successful at detecting leaks within the city. Now, another fiber path that we have in the city of Perth is an 80-kilometer fiber loop on a dual-channel interrogator that we've just installed, and this is a multi-use fiber deployment. Now, what we've done here is actually we've detected a magnitude 3.7 event about 173 kilometers from the city. Right, so we can call this a regional earthquake. The data that you're seeing here, this is from that magnitude 3.7, and that these top arrivals here, this top section, these are the P waves. These are the P waves that first arrive being felt by that earthquake. This is all being processed down sub 4 hertz, or sub 5 hertz, sorry. This section down here, you can see a very clear S wave arrival, and then some beautiful surface waves showing up. To zoom in on the top, you get to these beautiful P wave arrivals. Coming in, quite a lot of move out. Due to the geometry of the deployment, I mentioned this is the fiber path that we're sensing this on. The wave field is arriving in this general direction. So you can see the move out. So this is initial arrival and beautiful move out down to the center. Now, this has some implications, and this has some beautiful applications for infrastructure monitoring. If you start correlating the signal response or amplitude response with what's happening along that fiber over these 40 kilometers of fiber that we're showing here, you can start seeing things about ground competency. You can start making some inferences. If this fiber is perfectly coupled, and that is a big assumption, if this fiber is perfectly coupled for all 40 kilometers, and the ground conditions are the same, you would expect effectively a homogeneous amplitude response all the way through. That's not what we're seeing here. We're seeing some quite strong amplitudes in this section, quite strong amplitudes in this sections, so quite competent, quite strong rocks. On these edges here, it's a little bit different. It's a different story. It's quite a lot dimmer. So that means that the coupling is either not as good, or that the ground conditions are more or less conducive to transmitting seismic waves. This one shows it quite well. Now, I'll note that there is quite a lot of noise in here. This is being acquired during a rain event. So these locations where you have vertical striping, these are drainage locations as well. So again, extremely rich data sets. You can start making inferences about the drainage systems. You can start making inferences about the geophysical or geotechnical rock properties. We can really start talking about quite a few different components here. Now, we haven't provided an interpretation for this, but we did go out to one site, and what we realized is that one of these sections here is in fact sitting on really sandy soils, effectively built on top of a sand dune. This entire section of the city was built on a sand dune. So you don't get a lot of vibration transmission out to this area of the fiber. Now this is standard telecommunications fiber sitting in a pit, in a conduit effectively. So this is not perfectly coupled to the ground, and even that way we're still able to detect an enormous amount of activity happening from a very small earthquake regionally. I think I will leave it there. If anybody has a question, please let us know.